Hey, good morning. Hey, good morning, good afternoon, and good evening, everyone. How are you guys?
I'm doing really well, thank you. It's been a good week.
Okay. Yeah?
Yeah.
Cool. Are you ready for today's session?
Yes, definitely. I'm actually really excited about it because we kind of get to the complex math, but I'm kind of hoping to keep it simple and understandable nevertheless. So we'll see how that goes.
Yeah,
And
that's a good idea.
we should probably also say to our viewers who didn't see the first episode that you can see all of the episode on our YouTube channel. So if you missed out on the first one, you can just go back and see it in your own time, and then you can come back and watch this episode.
Yes.
Yeah.
Okay. Heini, would you like to tell us a bit about what you're going to talk about today?
Yeah, sure. So today our kind of main topic is calculus, and it might be one of those topics that people have come across while they've been in school. And it might not be people's favorite topic because it does get kind of heavy and complex and all that. But calculus is one of the areas that is really heavily used in data science and machine learning and all that in many different situations, both in like tuning algorithms and probabilities and things like that. So it's really important. But so I will kind of try today to take the parts that we need to understand, not so much go into the details of how you calculate it, but kind of just go through what we should understand about on the calculus side. And definitely this session will be building on the previous one, but I'll have kind of in the beginning a little recap of what we went through last time. So even if you missed the previous session, you might be totally okay to jump on board. So
That's cool. And that's cool that we have a recap before starting on calculus as well. But for those who would like to check out the previous recording from the previous session, that was about algebra with Heini, we will share the link later on where you can see this recording as well. Håkan, do you think we are ready to go?
Yeah, I think we can have an introduction here to AI42 in a short while here.
So hi and welcome everyone to today's sessions. And before we get started with mathematics, let us say a few words about AI42. What is our movement and our motivation, and what we are going to present you and the following few months as well. So Håkan, would you like to get started?
Yes, so the basic idea here with AI42 is we would like to give everyone here a chance to get into artificial intelligence, machine learning, and data science. And in order to do that, what we have done is we've invited industry experts and recognized speakers. So they will have sessions here 2 times a month. So we will be streaming them onto both Facebook and YouTube and on Twitch and on Twitter.
Yeah, exactly. And sorry, I just wanted to mention and that the idea is that we would like to bring you through the path to become a data scientist or an AI engineer in the end. And we are doing so that we are providing, so as Håkan said, first mathematics, then statistics, probability calculations, and then a lot of different coding languages we are going to present you as well. And at our sessions, you can learn all these if you want, and you can get to be a really good data scientist in the end.
Yes. And then for information here, you can see we're available here on Instagram, on Twitter and Facebook. And if you want to, you can scan our QR code to get into our YouTube page or our meetup page. And we'll also post these links in the chat later on in this session. So Eve, do you want to say something about our sponsor?
Yes, first of all, we want to say thank you to Microsoft for sponsoring us, and also for saying thank you for contributing with us on all the graphics and the music and all that we are doing here to Levente Pongor and Mina as well. We also would like to say a big thank you for all those communities who are supporting us in any ways. Here I have to mention also Global AI community, who are also supporting us in many ways.
Yes. Yeah, so then I think we can go back to Heini.
Hi, Heini. Welcome
Hello.
back.
Thank you.
I think as someone commented actually in the chat just now that complex math and excited in the same sentence is really make this a very interesting session today. And I think we are about to get started. So how do we have something else we should mention before starting?
No, yes, just if you have any questions at all during the session, feel free to post it in the chat, and then we will take the question after the session. We will have a Q&A session.
Yes.
So then we just will leave the floor here to Heini.
Perfect. So good evening, everybody, also from my behalf. It is the second mathematics session here in AI 42, and tonight's topic will be calculus. And in regards to calculus, you might have heard about things like derivatives and integrals and minimums and things like that. And they might be some of those topics that can be a little frightening even, because they are quite complex, and especially the side of really making the calculations in those areas. So what we're going to be focusing on today is mainly understanding what those concepts of calculus are and how we can then use them in different areas of data science and machine learning as well. And as mentioned in the previous session, we went through kind of basic algebra. We started by going through things like looking at data sets, because data sets are what we're working with when we're doing anything with data. And then we started looking at how can we explore those data sets. So we looked at some unions and how we can explore those data sets that we're using. But then we also started to get into equations, and we ended up with functions. And really kind of what we were basing everything on was this idea of, well, if we have some kind of data set around, and we want to have some kind of algorithm and find out that line that will be the most optimal for us to explain how this data behaves. But the question still is, even after previous week's session, is how do we actually find that line? And so today we will be, of course, basing everything that we do on the basic algebra that we started with 2 weeks ago. And today we will be going into the calculus, which will be then looking more at kind of how do those functions change and really examining those functions in some specific manners. And by doing that, then we will be able to get closer to answering that question of how do we find that line in our picture. But after this session, we're also going to have 3 more sessions regarding mathematics also. And all those will kind of help us go towards those more complex scenarios as well. So we're going to be building still on top of this week's information as well as we go along. And so that you just know what is coming along as we go in this journey towards data science and machine learning in regards to math, The next session will be around linear algebra. And then after that, we will be looking at statistics. And then as the last part, we will be looking at probabilities. So if you have not met me before, I am Heini Introduction. I work currently as a DevOps consultant in Polar Squad. I actually changed jobs since the last time we did a session. So it's been kind of very interesting and exciting times for me. I am a Microsoft certified trainer, and I have been doing a lot of Azure training in the past years. My kind of favorite topic around Azure and all that is pretty much architecture and data. That's kind of my passion. But I used to be a mathematician, and that is what I studied. And that's kind of one part that cannot be taken out of me in that way. And yes, if somebody commented that it's weird to say complex math and excited in the same sentence, yeah, that kind of describes me, actually. And the other thing that you will see is that I am a bit of a serial doodler. You will see some of these pictures all throughout the session today. So to just give you an overview of what we will be covering today is that we will kind of start with what we left off last time and kind of go further into what can we do with those things that we looked at in the previous session. We will start with kind of looking at equations of functions first, so doing a little recap of what we ended up with last time. And then we will look at some special functions and why we need to know about these. After that is when we will be going into the actual kind of main calculus part. And that means that first we're going to be looking at derivatives. Then as the second point, we will be looking at minima and maxima. And then also looking at concave or convex functions in a defined interval, so finding saddle points. That might not say much at this point, but don't worry, we'll come back to this. And then as the last portion of today, we will be looking at integrals. So let's start with just looking at some equations of functions and what do they look like. So we finished off our previous mathematics session with looking at kind of transformations on functions and how they act when we change those functions a little bit. And one of the most common functions that we might look at is just straight lines. They're simple, they're nice and straightforward. There's not so much complexity to those. And there is actually a format at which those equations of straight lines will always be at. And that is that it will be y equals ax plus b, where the a and the b will be some kind of numbers. And for example, if we wanted to know the function or the equation for this function that is shown in this graph, we could kind of look at this picture and try to find out what those a and b must be for us. And just a moment here. Just gonna grab my pen here. And so if we look at this graph that we have here, we can see that, for example, our graph cuts the y-axis at 3. So what does that tell us? That tells us that when x is 0, y equals 3. And so because of that, we actually gain some information about this line. But we need some more information to be able to determine that equation that we have. So for example, when we go from the 0 to number 1 on the x-axis, we find out that the y-axis value pops up to 5. I just missed that. So we can find like that. And so whenever we take one step on the x-axis, we go from 0 to 1. Also, our y value goes from 3 to 5, so it doubles. So actually what these two pieces of information are telling to us is that we can kind of how fast this straight changes is by 2, and that becomes our multiplication value here in front of the x. that tells how fast does the straight line go up as we take one step on the x-axis. And then the number 3 here actually tells us where we are crossing the y-axis with our line. So that is what were able to read from there. And we can use this method to find the equation of any straight line that we're looking at. And if you remember, at the end of the previous session, we were looking at how by adding, kind of changing that function that we have, we transform the line. So for example, having a +5 at the end instead of a +3 will pull our line up. It will kind of take it up the y-axis. Or changing the multiplication value in front of the x, which is 2 currently, changing that will also change the slope of the straight line as well. So by changing these values of a and b in this function, we change what kind of line this is. But what is common for all of these straight lines that we're looking at? We can say about them that they are actually directly proportional. That is a hard word to say for some reason. And what that means is that the relationship between y and x is constant. And another way to say that would be that whenever x changes a certain amount, the y changes in the same proportion. So that is why we get a straight line. So for example, we are working with straight lines, for example, when we are fitting that linear regression model in our data set. We are working with straight lines. We're trying to change the a and the b in our linear function to find the best possible line to fit with our data points. So that is one kind of functions that we can look at. But there are many, many different kinds of functions. And with some other functions and their graphical viewpoints, it might be much harder to kind of figure out the function just looking at the graph. And that's okay. Kind of the point of looking at these different kinds of function is just kind of getting a sense of how they look when they're mapped out, when they're graphed out. So for example, in this picture, we have a function that is y equals 2 divided by x. And this might not be as obvious, but we can kind of check it out in this picture that we have here. And if we look at this one, if we, for example, take the value of x at the number 2, we can find that the value of y at that point is 1. That's where it crosses. There we go. So if we take 2 divided by 2, since the value of x is 2, we get 1, which is the y. And if we kind of take other points here, we find that when the value of x is 4, the value of y is actually a half. So we kind of see that, okay, it actually does fit this function that we have here describing this. And this is just another type of function. And for this type of function, actually, we have a special name for these situations as well. And these are the other type of proportionality that we have. And in this case, x and y are actually inversely proportional. And what that means is that instead of the relationship between y and x being constant, it is actually the multiplication of x times y is constant. So actually in this case, whenever we take the value of x and the value of y from these curves, that will always be 2. So here are just 2 different kinds of pictures that we can look at. There are other kinds of functions that are also used in data science and machine learning. And we're just going to take a quick look at some of these and what they look like. So we're, for example, going to be looking at the logarithmic function. We're going to be looking at x squared. So when we have this situation that we square something, then we're going to look at the cosine function, cosine x. And then we're also going to look at kind of this division situation when where we're dividing by x squared. And then as the last point, we're going to look at the tangent as well. And since these would be a little difficult to draw, I'm actually going to use this GeoGebra drawing program that we were also using last time that we were going through these. So let's just go in there and draw some functions. As you can actually see, I had the previous function here that we were working with, and you can see how it maps out in the axis system. So, but I'm going to delete that one, and let's just start with one of the functions that we have. So I'm going to need this one here, and we're going to need that one. So the first function that we're going to be looking at is the one of the logarithmic functions. And just remember, in mathematics, we have these certain areas where we're representing something in a shorter way. So we're not going to go into details what this specifically means, this ln in the equation, but we're more interested about how does that look as a graph. So if we look at this graph, it creates this curve where whenever it starts to go on the x-axis below 1, it starts to get closer and closer to the y-axis. And then it slowly keeps getting bigger and bigger and bigger as the value of x grows. And again, if we wanted to do some kind of transformations on this one, we could, for example, multiply this equation by 2. And we can see that it immediately starts to grow much faster than in the previous case. So again, we are able to do these transformations, whatever the function is like. And one important aspect of why we're looking at these functions is that because we cannot always use straight lines in all situations. We might have situations where our data is not linear. It's not kind of in these nice patterns around a straight line. And we might need to look at some kind of other kind of model to understand our data. But we also want to look at other kinds of functions. The second one that we had was y equals x squared. And as you can see, it's quite a different kind of function. Let's just hide the other one. This is something that you might have come across and heard the term parabola. So the x squared function always kind of gives this parabola shape where we have a minimum value somewhere facing down. Though if we wanted to, for example, flip this, we could kind of multiply this by -1. And again, we are working with the transformations that we finished with the previous session. So whenever you see this kind of bowl shape, you're most likely, you know that it's kind of this second degree function. If we instead wanted to, let's say we want to look at a third degree function, we have, no, wrong one, sorry about that, this one. That looks right away completely different. So depending on what kind of function we have and what we're doing with the variables in that function, the shape will change significantly. And you just want to get familiar with which shape corresponds to what kind of function. Because there is always that similar shape if you find, for example, the x to the third in that function, then it will be similar to this shape here. Then we also had something called a cosine function in the ones that we were looking at. And again, I'm going to find that here. And this is, again, something completely different. The cosine function is interesting because this is a function that will alternate between 1 and -1 in kind of the most simple form that we have. And it is this kind of continuously going through the same pattern. So it will just alternate between two values in a very kind of predictable way. And this can be also useful to us in the future. And then as the last option here, we're going to look at the tan function. And the cosine and tan are both trigonometric functions. So they go into that category. And the tan function is very different. It again has this repetitive pattern that also the cosine function has. But instead of going between a 1 and a -1, it actually always goes toward kind of infinity at the points between the intersection points on the x-axis. So as you can see, with functions, we can get very many different kinds of shapes. And it's just useful to know that, okay, when I see this kind of function, I know that it has that third power in the x portion. Or if I see this bowl, whether it's facing down or facing up, I know it's a parabola, and it is kind of these situations where you can find the x squared in there. There are many variations of these. So for example, here could be more values within it. See that? Again, we can move it up or down, make it wider or narrower, etc. So the shapes will transform as that basic form of the function transforms as well. And why are we going through these functions? Well, we're going to come across these functions, for example, when we're going to be looking at things like minimizing, when we're tuning our algorithm and trying to minimize the error of that algorithm. We, for example, come across the x squared based function. So we will come across these different kinds of functions in many different scenarios when we start to explore data science and machine learning algorithms and things like that. So I really recommend you to just kind of get familiar with the different kinds of functions and what they look like, and kind of how do they act? How do you change them? How do they transform? But when we then have these functions, we might need to know some more information about these. And calculus has to do with looking at the changes in functions. And one aspect of calculus is derivatives. And what derivatives is about is the derivatives are like looking at the changes of our functions. So really it is looking at the slope of the function. And what this really means that it looks at how steep is it. And if we're looking at our picture of a straight line, the steepness of that is always the same. It stays constant. If we take a point from the x-axis at number, let's say, we take a point from the x-axis here at 2, and we look at that point, the slope is the same as the line. If we take a point from the x-axis at -2, yes, it's going to be exactly towards the same direction, the steepness of that straight line. So straight lines are kind of easy. It's always the same steepness. But where the interesting thing comes in regards to derivatives is when we look at these different shapes of functions. And in this case, we're just going to look at kind of this. We're not going to care about the function itself or the equation of the function at this point. We're just going to be looking at this nice curve in our coordinate system and look at what does the derivative tell us. So in regards to derivatives, the derivative is talking about how steep is the curve or the line that we're looking at. So if we look at this picture and we just randomly pick a point from our curve here. I think I need to change my color because otherwise you're not going to see anything. If we pick a point here, the steepness of it will be going up at about this kind of angle. So that's just roughly. But if we pick a point back here, the steepness is going to be something like this at that one point. So really, a derivative at a certain point is looking at how steep is this curve at this specific point. So we have, for example, on the left side here where we drew the point, the steepness is going slightly down. So it is kind of going downwards a little bit. And in this case, it means that the derivative is below 0. So the derivative will be below 0 whenever the steepness is going down as we go left to right on the x-axis. And on the other hand here, the other point that we drew, since the slope is going up, this means that the derivative will be above 0. So it will be a positive number. And since it is actually at this right-hand side point that we drew here, it is bigger, it is kind of steeper than the point that we drew on the left. That means that derivative value will also be bigger. So for example, it could be something like, well, the right-hand side is 3 and the left-hand side is -1, for example. So it's just a rough estimate based on the picture. But we also have these kind of tops of hills. And actually, if we pick a point from the very top here, there we go, and we draw the line that describes the steepness of that one, it kind of ends up being this flat line, if I just could draw it flat. So don't mind me not being able to draw a flat line there. But that's about how the steepness would end up being as we go up that hill and we hit the very top of that curve. It will lay flat. So whenever we have these kind of top or bottom points, in those points, the derivative is actually 0. So because it's not changing. For that one moment at the very top of the hill, it's completely flat. So you can kind of even think this in the way that you have like a marble rolling around this curve that we have. And so whenever that marble gets to the top of the hill, it will not move unless you push it a little bit and you give it some speed. And then as it does get rolling, the steeper the downhill gets, the faster it will roll. And then as it reaches a point where it's going to head uphill, it's going to slow down. And again, as it reaches the top, if it doesn't have any speed, it's just going to stop there because it's flat for a moment there. So the points where the derivative is 0, those are kind of the flat points on the curve. So really looking at these derivatives, what it allows us to do is find these top and bottom points on our curves. So if we kind of take a blank slate here and look at the same situation and try to find the points where our derivatives are 0, we can find them here about, it's interesting with hand-drawn pictures because they're not kind of perfect. So it's about there somewhere. We have a flat point. We have a flat point about there. And we have a flat point about there. And so these are what are called minimus and maximus, maximum points and minimum points. So here, I'm going to grab another color. So we have a maxima point here, and the other one over there. And here we have a minima. And even more so, there are these kind of, these minimum and maximum points can be either local or they can be global. And what that means is that a global maximum point is the very like highest flat point on that whole curve. So for example, this one here is a global maxima because it is the largest point on that curve. We don't actually, because we don't have the whole curve mapped out, we don't know whether it's the global maxima, but just looking at this part that we have visible here. But the minima that we have in this picture, it's not a global minimum because, for example, here on the right, this curve goes even to a lower value than that one in the middle that we have marked. So really, by using derivatives, we can look at the steepness of the curve. We can look at, is it going up or is it going down? And combining that information with the knowledge of where are the points where the derivatives are zero and finding the minima and maxima, we can gain a whole lot of knowledge of how does this curve kind of move around. So we can even put it in this kind of a box-like form here, that if we would like to kind of take these points into this graph, we know that there is, let's just call it 0.1. It's not actually 1 on the graph, but we have 0.1, we have the 0.2, and we have the 0.3 there. So we're just going to mark those here. And if we look at the derivatives before these points and between each of these points that we have here as the minimas and maximums and as the points where their derivative is zero, then we are able to kind of map out how this function acts. So if we take a point from here, from before this first maxima point that we have here, and we look at the derivative, we can kind of see that it's going up and it's a plus value because it is going up. And so we know that our curve is heading up. If we look at the derivative here in between, we can see that it's heading down. So it's a minus value derivative. And that means that our function is going down. If we again take a point from between the 2 and 3, then we can find that it's heading up. It's a plus value again. And then we can find again that, okay, it's heading down again. So it's a minus value. So by looking at the whether the derivatives are minus values or plus values, we're able to map out how does our function kind of traverse through the coordinate system. When is it reaching a top point and when is it reaching a bottom point? And of course, as we looked at the different kinds of functions, there are many kinds of forms that our functions can take on the graph. So how do we actually calculate these? And again, we're not quite going to go into the details here, but there are formulas to how these are calculated. And we're just going to take an example. And you don't have to remember these by heart, but it's just for your information that there are formulas for how you can calculate the derivatives. And we're just going to take one example here for calculating a derivative. So we're going to take a graph that we're going to draw here. We're going to have our coordinate system, and we're going to have a parabola here. And try to remember for a moment what was the equation for that one. Yes, it is the x squared one. So we're just going to say that this is y equals x squared. Yes, it's not a perfect picture, but we get the idea. And so we have this scenario where we have a power in that scenario. And so that means that from our list of formulas that we have here on the left, we can find that we can calculate derivative in this way. So it's telling us that if we are calculating the derivative, we're just going to copy it over so that you see it a little better because it's so small on the left. So here is our formula for calculating this. So in our case, so the first part here is just actually telling that, yes, you're doing differentiation. So you're taking the derivative of this function. So that's just kind of a way to tell you that's what we're doing. So we're going to take a derivative of x squared. And that means as the 2 is now our a, we're going to take the 2 in front. We're going to have x, and then we're going to have 2 minus 1 as the power. And since 2 minus 1 is 1, and power to the 1 is just the same as x, that means that we don't have to do anything other than that. The final answer for the derivative is 2x. And it can feel a little weird, like, okay, the derivative is talking about the slope and the kind of steepness of our curve. And how do we now get a straight line? Like, this looks like the equation of a straight line that we were looking at. But if you think about it, if we put into the place of x, if we put a 0, the derivative will be 2 times 0, which equals 0. So right here at the bottom, I'm going to need another color again. Right here at the bottom, the derivative is going to be 0. So it's going to be flat again. That is where our minimum is going to be. And then if we instead take a positive value there into the place of x, that means, for example, we do 2 times 4, it becomes 8, for example. And whatever positive value we put on the x side, it gives us a positive value. So we know the right side of the curve is always heading up. But instead, if we take a negative value into the place of x, then we are on the left side of the x-axis. That will end up being a negative value because 2 times minus 3 is, for example, minus 6. So it's going to be a negative value, and negative value meant that the curve is coming down. That's what the derivative is describing. So really, we get a formula that will tell us information about when will our derivative gain positive values and when will it gain negative values. And it will also help us find those situations where our function gets a 0 value for the derivative as well. So really find those minimums and maximums. As you can see for the parabola, for example, the point on the x equals 0, where the derivative gets a 0, that's also the minimum of that function in total. So remember here, the d divided by dx, that's just telling us that we're doing a differentiation. And then we can use any of these formulas that we might have to do that. And sometimes, for example, when you're doing tuning of machine learning algorithms, this might be happening on the background. And we'll be looking at that in just kind of brief overview way in just a moment. But I just wanted to point out before we get to the next topic that there are actually different ways that one can mark that you're doing a different differentiation. So sometimes we can also mark the functions like this. So this is essentially the same thing as y equals x squared. And sometimes derivative of this function is also marked as this little slash at the top between the f and parentheses. So this would mean just exactly the same thing. So really, again, as it's math, there can be different ways to mark things. So again, we could be looking at the having these different ways to mark this differentiation or derivatives. So how does this all relate to data science and machine learning? Where do we use this? So there are quite many places, but I'm just going to give you an example. So we're going to get back to our situation of us having our coordinate system and having a bunch of data points on that coordinate system. And what we're trying to do is trying to find the best optimal line in that coordinate system to be able to then use that equation to also predict when we get new data. So we're using this old data set to tune our algorithm. And then based on that algorithm that we find and the model that we find, then we're going to be able to predict. And as we were looking at before, remember, as we're working with a straight line, the equation will be something like y equals ax plus b. And so really that tuning of the algorithm is that we are changing around the values of a and b, making our line that is fitted into our data set, making that a little different, a little steeper, or we're moving it up a little bit, or moving it to the right, or whatever we need to do to make it the best possible fit for the data that we have. But how do we assess whether it's a good fit or not? And to do that, we have things called loss functions. And I'm just going to give a general overview of one of the types of loss functions that we can use. And one of these types is so that it looks at each of these values that we have here, and it looks at how far is it from the prediction. So it will look at how far is it from the line, how far are all these points from the line, because they should be coming as close as possible. And so what we will be doing is that how that loss function is formed is that we take the value of what was the actual value, we can mark that with y, and we take the value of the prediction, I'm just going to mark that yp, and we put that to the squared. And that might look a little familiar with. So of course, those values of what y minus yp ends up being will vary. So we can actually just simplify that. Yes, this is going to be a function that could be just informed by x squared. So what we're going to be doing then is, while we're tuning the algorithm and we're trying to find the best a's and b's, we're going to trying to be making this loss function as small as possible. We're trying to make this x squared as small as possible. And what that means is that I'm trying to figure out whether I can fit it in this picture. As you can remember, we were just looking at the parabola, which is the x squared shape. And what we will be doing with that is trying to find the very bottom point of that parabola. The tricky thing there is, because we're tuning the a's and the b's, that x squared is kind of, there is more like this entire 3D system of where that x squared is changing all the time. But what we're doing with all that is trying to get to the minimum value. And when we're doing that, we're actually using the derivatives at that point to trying to get to the bottom of the slope from our parabola, as you remember from our previous picture. So if we just make a very small picture here with our parabola, what we're trying to do in our machine learning tuning, we're trying to take little steps from one point to the next and trying to get as close to the bottom as possible, but also so that we're not over-tuning our algorithm either. So that's kind of where this all relates to algorithms and tuning algorithms and so on. So we've kind of gotten through the section in calculus regarding derivatives. What you should be taking away from this is that derivatives is talking about the slopes of functions. That is what you should be taking with you. The other very major part of calculus is integrals. And what integrals, on the other hand, are talking about is looking at the accumulation of quantities. And what that really means is that with integrals, we are looking at the areas that are kind of left in between our curves and the x-axis. So in this scenario here, we are looking at these areas that our curve separates from the x-axis. So we're calculating areas. So this is quite different from the derivatives, actually. Like, how do these link together? And it doesn't really seem that we could use this in any similar way as we're able to use derivatives in the data science side of things. So really where we will come back to integrals is when we talk about probability distributions. So because then we are looking at how our probabilities distributed and how they accumulate. This is very much related to that. And we'll come back to the probability side of things in the last session of the mathematics. So we'll kind of return to the specifics of how this applies to probabilities. But right now, we're just trying to grasp the idea of what are integrals about. So they are about finding the areas between a curve and a x-axis. And we can either calculate integrals in general to find, kind of similarly as we did with the derivatives, to find just a general function, or we can take an integral between, for example, 2 points that cross the x-axis and calculate the integral on that space. And that means that that integral calculation would give us the area of this part here. So it will give us that area specifically. It will not give us any kind of general function, but it will give us a specific area. And just as with derivatives, we have a bunch of kind of these formulas again that we can use to calculate integrals. And again, there is a different notation to how we also tell that we're doing integrals and we're doing integrating with our function. So we're going to take another example. We're kind of actually going to take the derivative that we ended up with in our previous example. So for example, we calculated the derivative of x squared and we ended up with 2x. So for our example, I want us to calculate the integral of 2x. And again, we have to go looking into our formulas and see whether we can find what we need. And oh yes, there it is. Here, right there. It was in the middle. I was expecting it to be at the top. So we're going to use, no, that's not actually the right one quite yet. We're kind of going to have to use two things together. So this one above it, and then the fourth one as well. And so what we're doing here to calculate the integral is that as the third line points, if we have a number variable, we can just take it in front of our integral sign. Again, this is just telling us that this is what we're calculating our integral on. And then we still have to calculate the integral of x. And if we use this formula that we have here, we're just going to take, we're going to keep the 2 in front, and then we're going to calculate here the u equals our x. And then as we have just x, we can think that the power of that is just 1. So then we get 1 plus 1 here. And then we also get 1 plus 1 here. So pretty much as we're calculating x to the power of 1, that is the x part is the u and the 1 is the m part. So if we then calculate this out, we have 2, and then we have x squared divided by 2. And in this case, we need to know that with multiplication and division, we can do those in any order that we'd like. And that means that we're only left with x squared. And I actually left one part out. If you notice in this fourth row, it is telling us to put a plus c here. Plus c. Plus c. Okay, what does that even mean? What is that telling us? The plus c means that as we integrate 2x, we kind of have this variability in it that we have to consider in regards to the kind of the function. And what you might notice here, as we did the derivative, we started from, let's write it here. We started with x squared. We did differentiation and took the derivative of that, and we ended up with 2x. And with the integral, on the other hand, we started with 2x, and we ended up with x squared plus c. Interesting. So actually, derivative and integral are kind of their opposite operations. So if you take a derivative of something, then from that derivative, if you then take the integral back, then you end up with the original function. What this c is here telling is that because the derivative for x squared is 2x, but also the derivative, for example, for x squared plus 1 is also 2x. So whatever additional terms we might have in this x squared part, it doesn't matter. Still, the integral will be 2x. So this is just taking that into consideration, actually. So that is kind of how we can calculate integrals, just using the formulas that we have, and just help that help kind of get an understanding. But again, with these formulas as well, you don't have to remember them by heart. It's enough you can always check them. How did they work, and so forth. So just to kind of take one step back before we head on to the next slide, I do want to remind you that, yes, integrals, what that is actually calculating for us is the area between the curve and the x-axis. So it gives us a formula that allows us to do that. And when we are concerned with these situations where we actually want to just, for example, calculate an area between certain points, what we want to do in that scenario is that we want to then take the integral that we get and then use the points that we're using to do that. And just a moment here. Slide there. There we go. So that I can just get this last point here. So if we do have this scenario of integrals where we want to calculate the area between certain points, then to do that, we're going to take our example that we were whoops. That was the first time today. Progress from the previous one. So we're going to take our rough hand-drawn picture here, and we're going to take our function of 2x that we were just working with, because we already calculated the integral for that. So it means we don't have to do that again. And let's say we just want to calculate the area between 0 and let's say 3. Let's say that is 3. What we want to do in that case, as we are calculating our integral, we mark it with, we're calculating it from 0 to 3. We still have our 2x that we're calculating here. We need to have this. And so what we first need to figure out, what is the integral? So we're going to have, just mark it differently. Again, this is kind of a mark telling that, yes, we just calculated the integral. And we're going to do the x squared. We can mark the c if we want to. We don't necessarily have to, and I'll just show you why. And what we then do, we take the 3 here and we put it in to the part of x. So we do 3 squared plus c. And then we minus from there by putting in the 0 squared plus c. So we take everything between the 3 and the 0, and we calculate all those together. And so what we get out of here is 3 squared plus c minus, that is just going to be 0. So what we're left with is c, and that means the c's get out of the picture, and what we're left with is just 9 as the area. And if we had an exact graph of this, we could actually check, like, well, does that at least roughly look right? And that would allow us to really kind of see that this actually works. So what we were calculating there was this area between the points 0 and 3 on this line, y equals 2x. And where this really comes in handy is when we are looking at those probability distributions later on, because often we have some kind of graph, and then we just have to know what is the probability of something, and we get to do that by using integrals and calculating that area between underneath the curve that we have describing the probability. So what you should be taking away from integrals is that they are allowing us to describe the area underneath curves that is kind of separated by the x-axis and the curve. And also the third point that you should be taking with you is that derivatives and integrals, they are their opposite operations. So we can kind of be moving between those two and going back and forth and ending up with the same equations as we come back from derivative to integral and then back from that integral to the derivative. So I know today got a little more heavy than last time, but know and trust that we will be coming back to these concepts in the following session so that it will be tying in with the practicality of things. So we will be going a little deeper into the situations of what about when we don't have just two variables in the equations. We're not just looking at x and y, but what if we have multiple? How do we act in those situations? Because that is much more common than these two-factor scenarios in machine learning situations or when we're doing data science. So we will be coming back to this. Just let this sink in, and whatever, we're going to be building on this and kind of helping you to take the little steps to really kind of understanding everything coming up. So thank you very much, everyone, for joining. I hope you enjoyed it. If you have any questions, I think they might have been gathered already. So we will have a little time here to then go through those as the last part. Thank you for having me. It was really fun, and I hope you all enjoyed it.
Hi, welcome back, everyone. Heini, that was amazing. I love the integral part, mostly.
Yes, I kind of remember that it's your favorite thing.
Yeah, I couldn't wait to see it finally. And I can see from the comments that it was not just me who enjoyed it a lot today, and most of the comments are stating that they can't wait to see us again. I mean, see you again to show us something cool again from mathematics. Wow, it was awesome, and thank you a lot. And again, like Heini also said, it is very, very important to remember the basics of mathematics, like we talked about today and last time as well, and we're gonna talk about it 2 weeks later again, because all the things needed for being a good data scientist, and I think for an AI engineer as well, it is to know these functions or the integrals, because this is going to give you the foundation of the whole thing.
Exactly.
So yeah.
And the thing is that most of the time, actually, because we have such cool tools nowadays, you don't really have to worry about making the calculations. So we have libraries that will do those in the background for us. So really kind of not, I know we went through some of those calculations as well today, but you don't have to kind of get caught up in that, because it's the most important just to understand what are we doing with, for example, the derivatives and integrals. And that will help us kind of just understand what is happening behind the scenes.
Yes, definitely.
Yeah, I'm just showcasing some comments here. We got one comment from Steven Simon. He said that this is very interesting.
Cool.
Also got some from D.H. Masher. Said it was a nice session. And Istvan says, thanks for the great presentation. Looking forward for the next session.
Perfect.
And Steven says again that this was really great.
I'm really happy
as
to
I
hear
said,
that.
yeah, it's really cool. Great job again, girl.
Thank you.
Yeah. And we don't have any questions, but I assume that it's could be because it was maybe it was a bit hardcore to see these things again, and I also was thinking that this is really nice, and it is like connected, and I can see the circle is coming back to itself, and like I can understand like how it works, but like it's difficult to ask a question here. But no worries, because we're gonna share the resources and some things that you can practice as well. All the things that Heini talked about today and last time as well. This is going to be available or at our website, which is going to be shared with you. Just remember to follow us on Twitter or Facebook.
Yes,
And oh yes, and also the recording is going to be available. Sorry.
Yeah. And then you will be able to see our next session will be on February 10 in 2 weeks.
And then we're going to talk about linear algebra.
Nice.
Yes.
Can't wait.
Yeah.
Nice. Yeah, so I think with that we can thank first of all Heini for having this great session, and also thank everyone who tuned in and looked at this session live, but also you who look at it later on our social media channels.
Yes, thank you for joining.
Thank you, everyone.